Welcome to this talk. I'm Vittorio Chiavegato, and I'm a PhD student from the University of Trento in Italy. I'm working with the LISA group in the laboratory, and my supervisor is Professor William Joseph Weber. So today I will talk about the observation of test mass charge fluctuations during continuous discharge. And this observation is done through a torsion pendulum. So first of all, I want to start by discussing why we care about the test mass charge. So here is a picture of the test mass of LISA, and you can see that around it there are 4 objects which are electrodes. So these electrodes will be present to apply small forces and sense the test mass position. So imagine the test mass is free falling in space. There will be cosmic rays hitting it and depositing some charge on it. And if we don't do anything, this charge will keep accumulating because the test mass has no way to discharge since it doesn't touch anything around it. So since there are a lot of voltages applied to the test mass and also stray voltages around, and these are usually noisy, this charge will interact with these voltages and will be a source of force noise. So if we call any of these voltage Vi and write down the expression for the test mass voltage that we see is made out of 2 terms. One is proportional to the charge, the other is proportional to these voltages we are applying. And then consider the fact that the force on the test mass is proportional to the difference between these voltages and the test mass voltage squared. Then it is easy to show that we have a contribution to the force noise, which is made of 2 components. You see, this is the force fluctuation. It can be done through a fluctuation of the test mass voltage or a fluctuation of the voltages that are around, but times what? The test mass voltage itself. So if this is too big because the charge is too big, for example, then this can become an important source of noise. And this was also measured during the flight of LISA Pathfinder, where the test mass was brought to 1 volt and an increase in noise was measured. So we need a way to discharge the test mass. And in LISA, what we do is we use a UV light. So we shine UV light. This extracts some electrons from the photoelectric effect. And in this way, we can extract some negative charge. But we could also think of adding it back by eliminating the electrode housing, for example. So the message is we can manipulate the test mass charge through this photoelectric effect. And we can think of doing that in 2 ways. The first one is a fast discharge. So we stop the measurements, we measure the charge of the test mass, and we discharge it. And this was done in LISA Pathfinder every approximately 2 weeks. But we know that in LISA, we would like to measure for long periods of time, so we don't want to interrupt science. And so we will likely use what is called the continuous discharge, where we use continuous pulses of UV light that can keep the test mass voltage around 0. But my question is, are we really allowed to leave the light on? So in other words, if we leave the light on, do we introduce some force noise? Unfortunately, the answer is yes, because this process here of electron emission is something like a Poissonian process. So it's a stochastic one. And this will cause some fluctuations in the charge of the test mass. But we saw in the previous slides that the fluctuation of the test mass charge are important when looking at the force noise. So you see they appear here. So we must verify that these fluctuations are not too big and become an important source of noise. To test this, we use a torsion pendulum here in Trento. You can see here a picture of it. Down here, there's the test mass and the electrode housing. The test mass is hanging from a silica fiber of 0.1 millimeters diameter. And with this pendulum, we can study the torque noise, which we can then convert to an acceleration noise to compare with LISA and LISA Pathfinder. We have a sensitivity of 1 femtonewton meter per root hertz at resonance. And here is a comparison of the sensitivities of our pendulum, which is this curve here, with respect to the requirements of LISA Pathfinder, and also the performance of LISA Pathfinder. You see, we are a factor 500 from the LISA Pathfinder performance. So with this pendulum, we can measure the test mass charge with an appropriate technique and monitor it in time so that we can see the noise that UV light introduces, for example. So here I want to show you how a discharge of the test mass looks like. So this picture represents, you see a black line, which is representing what is called the injection voltage. It is a 100 kilohertz voltage that is imposed on the test mass for sensing purpose. Then there are these 1 microsecond pulses of UV light, and you see there's a certain phase between the injection voltage and the pulses. And if you use a scheme like this, what you can observe is something like what is shown in this plot here. Here you are seeing, maybe there's, okay, I'm sorry. Here you're seeing the voltage of the test mass as a function of time. And it looks like an exponential decay. So we can describe it with this formula here. And we can see that at some point we reach some kind of constant voltage, which we call equilibrium voltage. And this can be chosen by specifying the phase of the pulses with respect to the injection voltage. So we can choose this. And the first part instead, we said it's an exponential decay, and its time constant can be shown to be proportional to 1 over the power of UV light that we are using. And so how do we change the power of the UV light? For example, we can increase or decrease the pulse rate, like as shown in this picture. So the time constant that we'll probably use on LISA is around 1 day, because I will show you that with this, from a theoretical and experimental now point of view, it seems like it's one of the shortest time that doesn't introduce appreciable force noise. So let's suppose we put ourselves in a condition where the test mass charge is constant, and then leave the UV light on and measure the noise. So here I show you a comparison of 2 time series in which one represents when the UV light is off and the other one is when the UV light is on. So if I show you the power spectral densities of these 2 time series, you can see that we clearly resolve the noise when the UV light is on with respect to when it is off. So we resolve the noise over the background. The background here is determined by the sensitivity of our pendulum and by the voltage noise of the electronics controlling the pendulum. So then also it is important to show that this curve here seems to follow a 1 over f squared behavior. Its power spectral density seems to do that, which actually is what you expect from a Poissonian process of this type. And you can see I'm describing this power spectral density through this parameter here, which is a rate of exchange of charges between test mass and electrode housing. So it's a parameter that can be used to describe this noise. And this noise, again, is proportional to how much power we are putting in the UV light and to 1 over the discharge time. So putting all these together, what we expect is that this charging rate is proportional to the inverse of the discharge time. So we tried also to verify this, and to do this, we just repeated the noise measurement for many UV powers. And here is a summary of all the measurement campaign up to now, and fitting all the spectra that we found of the noise through a Monte Carlo fit for the rate parameters. What we obtained is this plot on the right, where you are seeing the charging rate as a function of the discharge time. First of all, I want to observe that the maximum level of noise allowed for LISA is this one. And you can see that when I choose a discharge time of 1 day, I'm lower than that level. So we are observing that if we use this discharge time, we are lower than a level that makes this noise important for LISA. And also you can see that here we find that 1 over tau behavior of the charging rate. So these are the two main results of the analysis. This is obviously still ongoing since we are trying to investigate some problems. For example, down here at high powers and low frequencies, we could be dominated by other sources of noise, different from the Poissonian ones. For example, fluctuations in the phase of the pulses. But more importantly, I showed you before that I told you before that we measure the noise while the test mass voltage is constant. But you can see from this plot that the voltage is not constant. It seems to be linearly drifting. And this linear drift is worse when we increase the power of the UV light. So we are asking ourselves, why is that? And we are not currently able to answer that. And the possibility could be that are we really maybe modifying the surfaces that we are shining with the UV light? And this is not very likely, but or as our apparatus some dielectric in it, and this is charging up and we are not able to discharge it back, we don't know. We are hoping to be able to answer this question soon. And this is everything I wanted to say about this work. So I thank you for the attention.